portion. And the central theme of that topic is this idea of force. The force. And to do this properly, of course, there is this free body diagram. And the free body diagram is essentially the summary of all the different forces or all the different interesting physics that are actually going on in that specific scenario. And then we can use Newton's second law to get us the acceleration, and then it can give us the different kinematic parameters that we're actually looking for. And so in this section, we began off cataloging all the different forces that you guys need to be aware of. And then we started going a little bit deeper into a few of the different forces. The first one was gravity, and that's on the side here. And then the next one was this idea of friction. So we're still delving deeper into some of these few forces. Essentially, what we're going to be doing is we are going to be doing an example using friction, and then we're going to move on to drag. And that's what I hope to cover for today. Now, regarding friction, let's recap where we finished off. Was it on the previous slide? Yeah. Regarding friction, there was the three different kinds. The static is when the velocity is zero, you're not actually moving. And the actual frictional force that is actually operating on the system does not have a specific algebraic relationship. You actually have to look at all the other forces, and essentially the static friction is going to be opposing all of that so that the net force on the system is going to be equal to zero. However, the maximum frictional force allowed did have a specific relationship, which you just needed the static coefficient of friction, or the coefficient of static friction right here, the mu, times the normal force n. Kinetic friction and rolling friction, well, rolling friction is just a subset of the kinetic, and that is going to have a very similar looking form of mu k times the normal force n. Okay. So with that in mind, let's do two examples. The first example, the primary question we want to ask or answer is how far does the box slide? Okay. So this is the scenario. Let's say Carol pushes a 100 kilogram wooden box on snow at 5.0 meters per second. The first question is essentially how swole is Carol? So how much force does Carol exert? And the second question, that's the question that we are really trying to get to, is if she stops pushing, how far will the box slide? So that's the question. So let's draw a little sketch so we have the correct scenario in mind. Carol is pushing a box. There we go. And so let's answer the first question. How much force does Carol exert? How much force does Carol exert? Essentially, the question is asking the push force is equal to what? The push force is equal to what? And for this, we need to draw the free body diagram. What are all the forces acting on Carol? Or not Carol, the box. The box is going to be our object of interest. So you have the force of gravity. You have the normal force. Carol is pushing the box. And of course, we have some friction resisting our motion. So this is F, we'll call it F sub K. So to answer this question, we want to begin with the force balance. The force balance. We can do the force balance in the x or the y component. But which one should we begin? With which one should we begin? Well, if we're looking for F push, what direction is F push acting in? Right, it will be in the x direction. So let's just begin there instead of focusing on the y. The net force in the x direction, we have F push acting in the positive x, so it's positive F push. And we have friction opposing it because it's in the negative x direction, so this will be minus the kinetic frictional force Fk. And from second law, we know that this has to equal mass times the acceleration in the x direction. In this scenario, what is the acceleration of the box?
5%.
This is speed.
0.
So what's the acceleration? 0. It's moving at constant speed of 5 meters per second. So this is going to be equal to 0. Therefore, this is equal to 0. So from our x component force balance, we get F push is equal to the kinetic frictional force Fk. Essentially, all Carol is doing is overcoming the kinetic frictional force that the ground is applying. That's what Carol's doing. That's all she has to do to maintain the speed. We just discussed the algebraic form for the kinetic friction is mu k times F. Now, when you have things like this specified, wooden box and snow, I'm going to give these information to you. So we are going to know these two values. Okay, that's part of our know. All you have to do is look on the table and then just read off the correct entry. So if we assess, do we know each term? Well, we know the mu sub k, but do we know what the normal force is?
Is it the opposite of force of gravity?
Is it? You don't know yet. All right, so that's ultimately the point. Although it may look like that. Well, you don't know it yet, so we don't know. So to actually get the answer to the first question, all we need is a normal force N. Luckily, we didn't fully exhaust all of the information that we have accessible because we only considered the x direction. We also have the y direction that we can utilize. And if you just look at the y, look what's up here, right? That's that normal force we are looking for. And as long as we can get n, we would solve the we would solve the problem. And we notice that the normal force is actually indeed in the y. So this was a promising approach, or promising second step. The force balance tells us that we have positive normal force, so that's plus n, that's in the upward direction. And we have force of gravity acting in the negative y direction, so it'll be this. And Newton's second law tells us that this has to equal mass times the acceleration in the y direction. In this scenario, what is the acceleration in the y direction? Yeah, is the box magically going off into outer space? Or is it magically just going straight down into a sinkhole? And both of those answers are no. So just from inspection, you come to the conclusion that this would have to be equal to 0. It's not going to be explicitly specified in the problem. That's just one of the natural consequences of you assessing the scenario. Okay. Meaning, from the net force in the y direction, we get the normal force is going to equal force of gravity as Sierra predicted. Well, you did it, you weren't 100% certain on it. Now you are. And so that is equal to mass times gravity. Now we know the normal force. We can plug it into our F push expression, where F push is equal to mu sub k times mg. Where the mu sub k from the table is going to be a value of 0.06 times the mass in this problem was 100 kilograms. Guys, how many pounds is that? Yeah.
220.
Yeah, 220 pound wooden box she's pushing. Times 9.8 meters per second. And so this is going to be equal to 58.8 newtons. Now, just to give you a sense of how strong this is, you can get a sense of this by dividing by 9.8. So someone divide this by 9.8 and give me the value. It should be like 5.50 or something. No. 5.6. 6. Oh, exactly 6. Even though the box weighs 100 kilograms, so that's 220 pounds, on snow, it's essentially she's lifting 12 pounds, or 6 kilograms. That's just like a kettlebell. That's how much force she's applying to maintain. So that's how low friction there is between wood and snow. Does that make sense? So I know this seemed kind of crazy, and she was probably like a bodybuilder, but now she's just, no, this is, yeah, like, I think all of you guys can do it, no problem. All right, but that's the first question. This is how much force Carol is pushing with. But we still have our actual primary goal of, well, we want to understand if she stops pushing, how far will the box actually slide? So let's answer the second question. Now, in the second question, we have to picture the scenario appropriately. So she threw it. So the box used to be right here. But then it's going to travel some distance and then stop. So we want to know this delta x. This is the delta x that we are looking for. How far does it go before it comes to a halt? So what we want is delta x is equal to what? But delta x at which condition? At what condition are we looking for? When are we actually going to say it has reached its final position? When what? Yes, we want it when the x component velocity is equal to 0. That's when we know it stopped moving and has come to a halt. Now the general approach is the following. We want delta x, and we can get delta x as long as we have the acceleration through the kinematic equations. But how do you get acceleration? Through Newton's second law and looking at the net force in the x direction. And this is the working backwards approach. Right? If you want to know this, you can get this as long as you have acceleration. Or you can get acceleration as long as you have the net force in the x direction. And can we get the net force in the x direction? Well, let's look at the free body diagram and that will tell us. Now the final scenario, this final sequence of events occurs after Carol releases the box. So she is no longer in contact with the box. So we have force of gravity down, we have normal force up. If Carol's no longer in contact with the box, do we have a F push? And the answer is no, because the push force has to have contact. And so the only force we have in the horizontal direction is the kinetic frictional force Fk. So remember, we wanted to see if we knew what F net x was. Well, let's see. Let's do the force balance on the x. And this is going to equal, well, we have a single force acting in the negative x direction, which is going to be negative Fk. And from Newton's second law, we know that this has to equal mass times acceleration in the x direction. So this is equal to negative mu k times n is equal to mass times acceleration. And so then the acceleration then is equal to negative mu n over m, or mu k, sorry. Now we just need to assess, do we know each parameter here? Do you know mu? Yes, we do. Right? We specified wooden box and on snow. Do we know the normal force? Do we know the normal force? All right, I saw shaking heads and then nodding and then. Who says we know the normal force? Raise your hand. Who says we don't know the normal force? Raise your hand. We don't know the normal force. You might be able to guess that it is going to be opposite the force of gravity, but we have a brand new free body diagram. At that point, you do have to recheck, did the normal force change, yes or no? So, we technically don't. And we just need to check. And for that, we look at the y component. So that the net force in the y direction, we have positive n minus force of gravity. That is going to be equal to 0. And from here, then you can deduce back that the normal force has not changed. But you can't just blindly say the normal force did not change. You should actually reconsider and rethink through this entire scenario. Did the y component, anything about the y component change, that thought should be crossing your mind. And then after you consider, you're like, actually nothing in the y direction has changed, so it actually is equal to mass times gravity, and then that's okay. So then with this, we get acceleration is negative mu k mg over m, and you can see that the g's cancel, and the acceleration is going to be mu k g. And when you plug it in, you'll get negative 0.588 meters per second squared. But this is not what the problem was asking for. The problem was asking for delta x. So now, delta x is equal to v naught x t plus 1/2 ax t squared. Now we just need to think, do we know all the different pieces of information? Do we know v naught x? The initial speed the box was moving? Yes, 5 meters per second. Do we know the time that it takes for the box to reach its final spot? And that answer is no. So we don't know the times, but we did just compute what that acceleration value will be. So the only thing we need is time, the duration. And for the duration, we just have to remind ourselves, we want this condition to be met. The final condition is when the x component of the velocity is going to be equal to 0. So Vx of t is equal to v naught x plus axt. That's just one of our kinematic equations. At the final time, this is going to equal 0, meaning t final is going to be negative v naught x over ax. Or this is negative 5 meters per second divided by negative 0.588 meters per second squared, which is equal to 8.5 seconds. Now we know the time. Now we know the duration. Delta x is equal to 5.0 meters per second times 8.5 seconds minus plus 1/2 times negative 0.588 meters per second squared times 8.5 seconds squared. And this is going to equal 21.3 meters. Any questions here? Yeah.
I don't know if I'm just not remembering, but where do you get the mu number from?
Oh,
Like the
you're
plane?
gonna be given it in a table.
Okay.
You just find it. You just wood, snow. All right. Here's the value.
So in a test, would it just be given and you guys
Yes.
it's this?
Yes. And I'll show you what that's going to look like on Wednesday. It's actually in the Canvas. It's called the handbook. I'm sure on modules you saw it somewhere, but there's a bunch of tables. One of them is going to be on there. And from here on out, I'll print you guys a copy on Wednesday, and that's the only copy I'll print you guys. So if you lose it or you disobey my orders, you're gonna have to print yourself a new one.
Okay.
But you're gonna be able to use that for every single quiz and exam from here on out. And that will summarize all the information that you will, and okay, everyone's always going to ask me approaching final, Do we need to memorize this? Are we going to be given this? You'll know exactly what you will have next to you in terms of that kind of information. You do not have to memorize that table because guess where it is? Right by your side, as long as you bring it. Right? As long as you bring it. But I don't want that to be a mystery, and I've compiled in a single document everything you'll need.
So like it'll say like wood on snow.
Correct.
This is the meal.
Or it might be like wood on ice, and then you'll have to say, okay, this is the closest one to my scenario.
Okay.
And then you use that because that's going to be your best guess.
Okay.
So clearly, if it was like rubber on rubber, or you should not read rubber on rubber entry if there's things like wood on ice.
Right.
Right, wood on ice is a lot closer to wood on snow than rubber to rubber.
Got
right?
it. Understood.
Yeah. But there's also things like metal to metal, and obviously that's also not this scenario either.
Right. Okay.
Alright, so this was a relatively, I would say, simple example. Let's do a slightly more difficult one. Let's say a 1,500 kilogram car is traveling at 30 meters per second. When driver slams on the brakes. And skids to a halt. And you're tasked with determining the stopping distance if traveling up 10 degrees, 0 degrees, or down 10 degrees. Yeah, you thought this was one example, huh? No, it's actually 3. Well, there's a reason why I want to do this example together. And it's because there's a smart way to approach this problem and a dumb way to approach this problem. What do you think a smart way of approaching this problem will be? And I'll give you a hint. The smart way, you do essentially 1/3 of the work. The dumb way, you have to do 3 times the work of the smart way. So which one do you want to do? The easy way, or the smart way, or the dumb way? The dumb way? Alright. No, you obviously want the smart way. And the reason why I wanted to do this example with you guys is to emphasize how important solving things algebraically is. And then plugging in at the very end. As long as you do it algebraically, you just do it once. And in the final expression, you're going to have thetas in your equation. And then you plug in theta is equal to 10, 0, and -10, and then you immediately have all of your answers. Or you can, a lot of you guys don't like doing the algebra, so you guys plug in early. Well, at that point, if you want to plug in early, you're going to have to do the problem 3 different times because you don't know how the theta actually changes your final solution. Okay. So the smart way, and I want to do the smart way with you guys, the smart approach, is to do symbolically. Essentially plug numbers last. And for those of you guys that are thinking, man, I still hate algebra, I'll just learn how to do this really, really quickly. I don't have to just give you 10, 0, or -10. I could say do from 0 to 90 at every 2 degree increments on a quiz. And if you choose to do the non-algebraic way, well, you might get 3 or 4 answers. And so you'll be, you won't do very good on that quiz. So instead, this is why I'm trying to emphasize how important this solving everything with symbolic variables is. And I want to go over that approach with you guys. And essentially, all you have to do is pick an arbitrary variable. So pick arbitrary variable for theta. So you don't consider one of the easiest cases, you actually just consider it to be, okay, one of the more difficult scenarios where you can actually specify an angle theta. So let's just consider a scenario when the car, you are breaking up some angle theta. We don't know what theta is yet. We don't know if it's 10, we don't know if it's 0, we know nothing. We're just keeping it theta, or being as generic as possible. And along this, we draw our free body diagram. Of course, we want to use the rotated axis, at which point this is theta. That's going to be force of gravity. This is going to be theta. What other forces do we have acting on our system? We have the normal force. And let's say the car was initially traveling up that way. And then the frictional force will be in this direction. And so this is what is meant by pick an arbitrary angle theta. You deliberately choose a scenario in which the theta is actually there. Then we can do our full analysis. Similar to the last problem, we wanted to know delta x is equal to question mark. And the condition is the same as before. It's when the final speed in the x direction is going to be equal to 0. So in doing this, we need, you know that as long as you have the acceleration, you can get your delta x. But to get your acceleration, you need the net force in the x direction. And of course here, the F net in the x direction, we always have our force balance that we can turn to. So let's begin here. So this is our positive x-axis, that is going to be our positive 1. So let's do the force balance in the x. So the net force in the x direction is we have negative frictional force Fk. Do we have anything else? Yes, we do. We have the force of gravity having a x component. So this is the force of gravity in the y. That is going to be force of gravity in x. So let's just draw that slightly more clearly. We have our right angle there. This is going to be our angle theta. Force of gravity, this is Fgx is going to be Fg sine of theta. So you did have to recognize that the force of gravity has an x squared component. This is the y because it's on the y-axis. This is or along the y direction. This is the x because you could see that it is in the x direction. It's going negative. It's going negative. So this is negative Fk minus Fg in the x direction. And from Newton's second law, we know that this has to equal mass times acceleration in the x direction. Or simply, this is equal to negative mu k times n minus mg sine of theta. Now let's also say we know you are also given the coefficient of kinetic friction. Let's say you're given mu. So we know mu sub k. Do we know the normal force? Is it going to be opposite gravity? Okay. We do not know the normal force. We know the mass. And the theta, we're just keeping it arbitrary, so we do know it. Now, this is a word of caution to everybody. The normal force is not equal to mg. Force of gravity is equal to mg. And this is another reason why I want to go over this example. The normal force will not be mg, and we're going to see that in just a moment. Yeah, question.
Sorry, I kind of got lost. Where did you get mg from?
Right here.
So that's not fg sine of theta, negative fg?
Yeah, but Fg is mg. That's the force of gravity.
That's just a thing.
We went over this last week. Yes,
I know,
force of gravity is mg.
Okay, cool. Just had to double check.
Yeah, the length of this is mg.
Yeah.
Yeah. So that's where that, remember this guy?
Yes.
You remember this thing?
Yes.
When this is the mass of the Earth, and when we're on the surface of the Earth, we use the radius of the Earth, and you combine these guys, so g times the mass of the Earth divided by the radius of the Earth squared, you get 9.8 meters per second squared.
Understood. Okay.
And so this is why it is equal to mg. That second mass is the mass of the object.
Right. Okay. I remember now.
And the x component of the gravity, that's where that sine of theta comes from, because we have the angle dependence from the fact that it's acting on a hill. So here we find ourselves needing the y component again, or sorry, the normal force again, and that is acting directly in the y. So if we do our force balance, all right, let me make sure, I got a text, let me make sure that's not my wife. It is not. This is the force balance in the y is equal to positive normal force N. And do we have anything else? Yes, we do. We have the y component of the force of gravity. And that's acting down. So it's minus Fg, except it's in the y direction. And so here in our force of gravity vectorization, Fg in the y direction is Fg cosine of theta. And of course, in using Newton's second law, we know that this has to equal mass times acceleration in the y direction. Well, what is the acceleration in the y direction in our scenario? Remember, our y direction is normal to the surface. Is the car magically going up and away, or down into the ground? The answer is no. So the acceleration in the y component is actually equal to 0. So then we get the normal force is going to be equal to Fg in the y direction which is going to be mg cosine of theta. And notice it is not just mg. There is the theta dependence because we are at an angle. The normal force is not mg. And right now we're looking for the acceleration right here. So then we can plug that expression here. So we get negative mu k times mg cosine of theta minus mg sine of theta. Oh, wait. This is positive. This is equal to mass times the acceleration in the x direction. And you can see that each term has mass, so we can cancel out a mass term. And so then the acceleration then is equal to negative. We can see that both of the terms here have a g, so we can factor that out of the expression as well. So it's negative g times mu k cosine of theta plus sine of theta. And this is the acceleration value. Once again, we don't want to plug in yet, or else we're going to have to do the problem 3 times, or maybe 45 times, or maybe 100 times, because I can ask you for all the different thetas that I wish. But now we have acceleration. We can now turn to our kinematic equation because we have a constant acceleration scenario where the acceleration is given by this expression here. It's just determined by the angle of inclination as well as how much friction you have. So it's a combination of gravity and friction. We know our initial speed, that's 30 meters per second. And we know our acceleration, that's given by this expression here. But do we know the duration of the halting step? And for that, we still do not know. So let's come back, and we're looking for the duration. The duration of what? The duration until the final velocity in the x direction is equal to 0. That is our final condition. So if we are looking for the time, then we turn to our velocity kinematic equation. And at t final, you know that the velocity is going to be equal to 0. So 0 is equal to v naught x plus ax t final, meaning t final is equal to negative v naught x over our acceleration value. This is how long it will take for the truck to come to a complete stop. Then we plug in this time, the duration value, into our delta x expression. So then delta x is equal to v naught x times negative v naught x over ax, because whatever is in the parentheses is our time, plus 1/2 ax times t squared. That's negative v naught x over ax squared. And here we're going to continue to simplify. This is equal to negative v naught x squared over ax plus 1/2 v naught x squared over ax. Alright, the square distributes to the numerator and the denominator, and we have one acceleration in the numerator, acceleration squared in the denominator. One of those are going to cancel. We're going to get this. And this is going to equal that, and that is the same. So essentially we have negative 1 plus a half, meaning it's negative 1/2 v naught x squared over ax. And we can finally substitute in our acceleration expression down into here, so we get negative 1/2 v naught x squared over negative g mu k cosine of theta plus sine of theta. Or if we clean it up a little bit, we see that there is a negative in the numerator and a negative in the denominator. So those will turn into positive, so we get v naught x squared divided by 2g mu k cosine of theta plus sine of theta. And we just need to reassess. Do we know all the different parameters? Do we know the initial speed? Yes, the truck was going 30 meters per second. Do we know g? Yes, that's always 9.8. Mu k? Yes, we said we know it. Do we know theta? Well, we have the three different thetas, 10, 0, and negative 10. And so we know these as well. And from here, you can easily make a theta and delta x table. For theta is equal to 10, delta x is equal to 30 meters per second, that squared, divided by 2 times 9.8 meters per second squared, times the mu value. Oh man, I forgot which mu value I used. Alright, so mu value, you would have been given this in the problem, times cosine of 10 plus sine of 10. And if you multiply all of this out with the proper mu value, you should have gotten, let's say, 48 meters. And at 0 degrees, you're plugging in 0 instead of 10. And so that'll change just the denominator. And so what you're going to get is 30 meters per second squared over 2 times 9.8 meters per second squared times mu k cosine of 0 plus sine of 0. And you're going to get a value of 57. And of course, you have it going downhill also. That's the last scenario. And here you would put in negative 10. So it would be cosine of negative 10 degrees, cosine of negative 10 degrees. If you do this, you would have gotten a value of, let's say, 75 meters. And once again, this is the benefit of solving things algebraically. And if you think, holy moly, this was a long problem to do, yes, that's my point. You don't want to do it 3 times, right? Right, that's the point. Just do it once, and then you can just plug in the different values for theta at the very end. Unfortunately, the problems are, this is, I wouldn't consider this on the difficult side of things. It's just you're doing it 3 different times. That's, I would say, where the challenge actually comes. So you're expected to do something along these similar lines to get here. Algebraically. Alright, any questions on this guy? So if you wanted to plug in very early, you really would have had to gone all the way here. Right, 3 times. And so the problem would have taken you very, very long. Yes, question?
I guess I'm still trying to understand mu, so how do you know? It's just depending on what the texture that the object is on, right?
Yes, and I would just give you the value. So it's
Right.
some number.
Okay. But, okay, yeah.
So you're just given it, there's really nothing to wrap your head around unless where you're actually getting stuck is the frictional force. But mu is just a mu. Like, what is mass?
Mass.
It's just mass, right? There's nothing more simple. Like, you can't break it down even further, that's just what it is.
Okay.
So if you're getting stuck on mu, you might actually be getting stuck on the frictional force, which depends on mu.
Okay.
But I don't know if that's where you're actually getting stuck.
Yeah, I think that's it. Because I thought that mu equaled some sort of formula, didn't it?
No, it didn't. Mu is
Oh,
just a
okay.
number. The normal force, the frictional force generally just looks like this. So sometimes it's called the fun equation. I hope you see why. So the mu you really have to be given, and there's, I'm sure there's technical ways of getting at the number, but these are mostly experimentally determined. Yeah, experimentally determined. And I might actually have you determine that in one of the labs. Maybe this is a foreshadow, I don't know. But yes, but it is experimentally determined, so there's no equation for you to memorize to actually compute it. You're just going to be given it because people have tried all the different combinations of surfaces. Yeah. Alright. So that's friction. And I would say, yes, friction is where the problems or meaningful problems can actually be asked. Because you have to consider a lot of different forces acting on the system, and you have to put it all together in a mathematically feasible fashion. But we still have 2 additional forces we're going to dig deeper into. One of them is drag, and the other one is springs. Drag is very, very complicated. And this is why I'm saying after friction, that's when we can ask meaningful stuff, because drag is way too hard. And I want to convince you of that. There is a reason why we pretty much always neglect drag in all of our problems. But I still expect you guys to know the conceptual aspects. And so even though you might not be computing it quantitatively, you'll still be aware of its existence and be able to speak about it in a conceptual fashion, in this broad perspective. So the third force we are going to delve deeper into is drag. What should we get the notation? Uppercase D. Now it's important to remember what the drag is. It is resistance from fluids. And some general things that we already discussed was the direction of this force. It is opposite V. Now, I hope you're seeing in the problems that we've done so far, the typical order, actually opposite V, one second. Because it opposes V, the drag depends on V. Because if the velocity is different, then your drag will also be changing. So drag depends on V. And it is this feature that makes drag extremely, extremely difficult to the point where you need above calculus to solve these problems. So calculus is not enough. So let me convince you of that. So typically, and I hope you've seen from the two examples that we've done so far, our force gives us our acceleration, right? From Newton's second law. Right, we wanted delta x, but we needed acceleration, but then to get acceleration, we looked at force. So it's the force that gave us our acceleration. And from acceleration, can we get the different kinematic parameters such as delta x as well as our v? This is the typical order of things. Unless you have drag. Why? Well, let's see. Your drag force will determine your acceleration. Well, yeah. That makes sense so far? The force can affect the acceleration. Then acceleration will tell you what velocity is. But if your velocity changes, that's going to change your drag. But then once you change your drag, that changes your acceleration. But then if that changes your acceleration, that's going to change your velocity. But then if that changes your velocity, your drag is being changed again. And do you guys see this kind of infinite spiral thing happening here? Yeah, and this is why calculus is not enough, and this is why we just say drag is negligible. Or all the problems that we are considering, we are going to consider when drag is negligible, because once you actually incorporate this into the mix, we actually don't have enough math to solve it in this class nor in the calculus-based class. So drag is actually extremely, extremely complex. However, that doesn't mean we just roll over and give up. There is actually a meaningful way of approach where we can still get some of these broad ideas out so that we still have a conceptual understanding of what's actually occurring. And so we can actually make some, qualitative predictions, let's say. Now, drag occurs when an object, so let's say this box, is moving through a fluid. The drag is going to be opposing V. So normally I would just stop the discussion here because hopefully I've convinced you guys drag is hard and we can't really move on. However, there is still a meaningful thing that I want to discuss with you guys, and that's why we're going to consider a little bit further. And that is the idea of making a simplified model. We can't actually fully comprehend this idea of drag with the mathematical tools that we have. Instead of trying to cover the entire spectrum, we can actually limit that scope a little bit and get a meaningful equation where it's just relevant in this very niche scenario. And that's the concept of making a model. And to do this, we just have to be aware of what are the main features or main variables on which drag depends. So what do you think? Just envision an object is moving with some velocity, but then you're going to have some drag. What do you think are some aspects that will determine how strong the drag resistance will be? What's one of them? Wind. Well, so wind is drag, so I guess that is true, but that's...
So then the speed of the drag?
we'll say speed of the object, the speed difference.
Okay.
Right? If the wind is moving 10 meters per second and you're moving 10 meters per second in the same direction, well, what's your speed? You're not moving. So we'll say speed. Speed is definitely one of them. So speed will affect the drag. And just to give you some experiential experiments that you can look back on, if you've ever ran, you'll know this idea, because it's the wind in your hair. The more wind, the more drag there is acting on you. Or you can hear the sound of the wind. If you're running fast enough, you can actually hear the wind whizzing past you, right? And it gets louder the faster you're going, and that would also tell you that drag is increasing as you go faster. So both of those features are echoing this idea. But what else would affect drag?
Air composition?
Huh?
Air composition?
Yes, we'll say density of the fluid. If you're moving through, in which medium is it easier to run? Water or air? Right, air is much easier, partly because of the density, so the density of the fluid matters. Anything else?
The surface area of the object that's in contact with the fluid.
Okay, size, but it's not necessarily surface area. In a very fundamental sense, yes, that is correct. However, in the model that we're trying to construct, there is a different way we actually consider, we break the surface area down into two different parts. One is into the size, and the other one would be into the shape. So this idea of the surface area that you mentioned, we actually break it up into two simpler ones, and the combination of the two will give you the surface area aspect. So this is a pretty comprehensive list, all the main things that actually will affect the drag acting on you if you were to, say, move through some medium. But we're trying to make a model here, and we're not trying to be infinitely precise. So we just want to do it for a very specific scenario. What scenario do you care about? And for us, we're going to limit that into the stuff that you guys experience on an everyday basis. So roughly, how fast are your interactions? How fast are objects moving in everyday objects? Like, what would be the fastest thing that you, on a daily basis?
A car.
Yeah, a car moves how fast? So we'll call it. So in terms of making a model, we actually limit each and every single aspect of this so that it's actually meaningful. In terms of speed, we want to use quote unquote human speed, right? This is what you guys interact with on a daily basis. And now let me tell you, just from having knowledge of additional classes and stuff, human speed can actually reach up to the speed of sound. So less than speed of sound. This is the speed range we are working with. Who knows what the speed of sound is? Huh? Mach 1? Yeah, but what is Mach 1? How fast is Mach 1?
So 3 times 10 to the power of 8.
No, that's speed of light. Speed of sound is roughly 400 miles per hour-ish, somewhere around there. So yes, this car is definitely within these bounds. And in terms of the physics, nothing changes until you get to approximately the speed of sound. So this model that we're making, okay, we want it to be, roughly human speed, 1 to 10 meters per second. But it turns out it's actually valid all the way up to roughly 300 meters per second. very, very fast. Now, density, aside from swimmers and fishermen, we just care about things that are moving in the air, right? So we'll limit the density to air. So object moving in air on Earth. What about the size? What are the size of objects you guys deal with on a regular basis? Just give me a size range.
The Earth.
Alright, that's true, but you're not seeing the drag on the Earth. Give me an approximate length.
6 feet.
Right, a few meters. Few meters in size. Oh man, we are running out of time. Also the shape. What shape? Well, the shape, this is where things get a little bit interesting. But for us, unless you're riding a parachute or throwing a frisbee, which is actually meant to take advantage of a lot of drag, so just not designed to maximize drag. Now, why the size comes into play, let me just ask you guys a question. This box moving, let's say in this direction. Where is the effects of drag actually occurring? If the fluid is moving this way,
On Earth.
no, yeah, but how drag is operating, drag is making it go that way, right? Why?
Pushing against something.
Pushing against something, what is that something?
The air. With
Yeah,
the
as the object is moving, the air particles are colliding this way, right? This isn't the only way in which drag operates. This is definitely one, so the air molecules collide and then they have to go around, right? Does that make sense? And so as the object is trying to move, it actually has to push the air out of its way. And you can see that that's not free, and it will slow you down. However, there is another way in which drag acts. And for you coffee and tea drinkers, you might know, if you guys ever played around with a teaspoon, what do you guys see whenever you play around with your teaspoon? What happens? Let's say you're swirling it, and then you get these little vortices or this tornado things, right? You guys ever see that? Next time, when you are trying to mix your sugar or whatever to actually make coffee edible, right? Just take your teaspoon and just go through the middle once, and then you're going to see if this is the direction your spoon went. You get these spirals forming. All right, hopefully at this point, do you guys know what I'm talking about? Yeah. This happens when an object actually moves. Right beforehand, the object was here, but it got moved to here. There is no gas particles over here. So, the air molecules right at the boundary is being sucked in to take the place. And this is what causes that spiral aspect. Do you guys see that? Can you guys visualize it? But here's the thing. How hard these particles are being pulled or pushed in here, that's actually pulling back on the system as well. So there's actually two ways in which drag actually works. Yes, it is hitting you from the front, but it's also pulling you from the back. And that's why the air is being pulled this way, but it's actually being pulled from both sides. And the reason why size is very significant is because as you get larger, the more and more of this is actually going to occur. And as more and more of this occurs, then this will actually dominate over this. And so I'm sure you guys know or have seen, these like very high-tech cars and stuff. They have these very aerodynamic shapes. Do you guys know what I'm talking about? This is the reason why you have this tail. It's so that it minimizes this back pulling. And so maybe you guys have seen this in 18-wheelers. So these typical 18-wheeler looks like this. Do you guys know what I'm talking about? More recently, there have been some additions added onto the back where it kind of looks like that. Do you guys know what I'm talking about? These little things, that flaps that come about. All it is literally a piece of metal. They just put it onto the sides and to the back of the very end, and it minimizes this. And immediately you're saving like 3 or 4 miles per gallon. Just by adding on these little, tails to the back.
So why do race cars, the ones that have the fancy tail on the back, like the extra height
like
things? But they're supposed to go faster, so why do they have? Yeah.
This tail?
Yeah. Why
This
do
is
they
for
have-
braking purposes.
Oh, okay.
This is for braking purposes. If without this, you would not be able to brake, or else they're immediately going to skid.
Ooh, dang.
This is actually meant to press down onto the car so that you can brake very, very quickly without skidding. I hope that's the only reason. I'm not an F1 car driver, so that is one of the main reasons. There might be a few more, but I'm not an F1 designer or driver, so I actually don't know all the reasons, but braking is one of the main reasons. There was a few more things I want to cover, but I haven't gotten there. But let me just tell you this. I can't give the problem thing.
Huh?
Hold on. You need this equation, right? Even though drag, let me just have just a few more minutes of your time. Even though drag is extremely complex, we can still do a few different calculations. So we can compute what is called the terminal speed. And this is the speed, the maximum stable, a stable max speed in free fall. Stable max speed in free fall. And this is that expression. Here, and we get this from the fact that drag is given this expression. It is equal to 1/2 rho, that density of the fluid is there. A, the size is there. V squared, that's the speed dependence. And then for the shape, that is the C. So rho is the density of fluid. A is defined as what is called the cross-sectional area. V is defined as the speed. And the C is the drag coefficient. And this has the shape dependence. This is where that shape comes in. Now, we need to be precise about this cross-sectional area, and this will be the last thing that I discuss. What is the cross-sectional area? For a sphere, let's say a sphere is moving in this direction. What is the cross-sectional area? Or what is the cross-sectional shape? It would be a circle. So the cross-sectional area is going to be pi r squared. But what about for a cylinder? A cylinder, if it's moving like this, what would be the cross-sectional area? The cross-sectional area is the shape that the air actually recognizes. So essentially, you take a flashlight from this angle, you point it backwards, what's the shadow going to be? What's going to look like? It'll look like a rectangle. That is correct. It will be this. The cross-sectional area will be a rectangle. But let's say we rotate this 90 degrees. We still have a cylinder, that same cylinder, but if it's moving this way, what will our cross-sectional area be? Cross-sectional shape. It would be a circle, and that is correct. And so for the area, we care about the cross-sectional area, not the total surface area or anything. It is the cross-sectional area of our object. So a car is approximated to be a rectangle because a car, let's say it looks like this. There you go. When you cut this right here, the shape you get is going to be roughly a rectangle. So even though car does protrude forward and backwards and stuff, we don't care about that. You just cut it in half, right down the middle, and what's the shape that you're going to make? And it's approximately rectangle. All right. Sorry I took a little bit longer of your time. I will see you guys Wednesday, maybe, or Thursday, maybe. But there will be a problem set due Wednesday. And if nothing changes, there will be a quiz on Thursday also, as well as a lab. Yes.
Could you zoom out a little bit, please? Okay, thank you. That's good.
I really hope it's for tomorrow.
The exams are finished grading. I have posted them on Canvas, but there's a button I gotta hit to unhide the grades or something like that.
Okay.
That's literally the only thing I have to do, but
Okay.
I don't know how to do it. I gotta figure it out. It'll take me like 5 minutes.
Alright. Wait, so just real quick. What you said about the
No, it's not because air spiraling. Air spiraling is an indication that